Reaction rates can be measured as the rate at which a product is produced or the rate at which a reactant is consumed. But oftentimes there are multiple reactants and/or products, so which one do we use when determining the reaction rate? Usually the answer is simply whichever one we can measure more easily in the lab. Not all substances can be easily measured. For example, if a neutralization reaction produces water, it would be essentially impossible to measure the production of water over time in an aqueous solution that already contains a bunch of water. We could, however, measure the amount of acid present by using a pH meter. So it would be more practical to measure the disappearance of acid rather than the production of water. But in fact, it doesn't really matter which one we measure, because the rates at which substances are used or produced are all relative to the reaction stoichiometry. Consider this example in which a solution initially contains 1 molar A and 2 molar B. 1A reacts with 2B to form 2C. If we look at the curves for A, the orange curve, and B, the blue curve, we see they don't fall at the same rate. B starts much higher than A, but by the end, they're much closer. This shows me that B is being consumed faster than A. Actually, it's being consumed twice as fast as A. This should make sense. 1 mole of A is consumed by the reaction when 2 moles of B are used up. What about the rate for C? We can see that C is produced at the same rate at which B is consumed. B and C both have stoichiometric coefficients of 2, so their rates are the same, but opposite in sign. And furthermore, we can see that their rates have a ratio of 1 to 2 to 2 that match their coefficients from the balanced equation. Here we can see that rates at which a reactant is consumed at various temperatures are also different. Which line do you think represents the reaction carried out under higher temperatures? The dark blue line shows the reaction being consumed more quickly. This reaction essentially finishes at around 7 to 8 minutes. At this point, there's no more reactant left. In fact, we can see that just after 1 minute, half of the reactant was already used up on the dark blue line. The middle line finishes around 16 minutes, and the light blue trial is still unfinished at 20 minutes. It would have finished around 50 minutes if I extended the x-axis. We could also alter the reaction rate by starting with more or less reactant. Here we can see that the light blue curve starts with 6 molar reactant concentration. It decreases at a rate of 1.8 molar per minute. The lower curve, which starts at only 2 molar, decreases at a lower rate of 0.6 molar per minute. So again, here we can see how reaction rate varies with reactant concentration graphically. In summary, reaction rates can be determined graphically by finding the slope of the line at any given time. Over a short time period, even a curve can be assumed to be linear. We can use the point slope formula. The rates at which reactants are consumed or products are produced are proportional to their stoichiometric coefficients. And lastly, altering the conditions, such as temperature or concentration, of a reaction can cause their concentration versus time curve to become steeper, which would be faster, or shallower, which means the reaction is slower. If you have any questions, please let me know via email or on Google Classroom. Have a good day.